So we'd like to write down something that would look like this. But the problem is on this side, this sign. Problem is on this side, I'd have a cosine function, and on this side, I have a sine function. And I don't have sines equal to cosines. So it's in this moment that Schrödinger realizes the complex numbers are involved. And that in fact, the solution for a free particle must look something like this. Where the exponential of this now imaginary number involves both sines and cosines. And this is easy to believe because when I take one time derivative, I just bring down the argument of an exponential by a chain rule. When I take two derivatives, I do the same thing again. It's still an exponential. So if complex numbers and exponentials of complex numbers are not very familiar, I suggest you take a look at this short tutorial on complex numbers at this time. And you can verify that the second derivative is just this. And the time derivative is just that. So both derivatives give me back something that's proportional to the original wave function. In other words, the second derivative with respect to x, which is minus p squared over h bar squared times psi. Well, I'm going to rewrite what p squared is. P squared is 2m times e, at least for a free particle. And I'm going to multiply and divide by minus I over h bar. That's all I've done here. The step from here to here is just having a minus I over h bar. Minus I over h bar. In other words, have something that looks like this. And that's Schrödinger's equation for a free particle. The left side is something like a kinetic energy. At least it will be once I take that second derivative. The right-hand side is something like an h bar omega equals E. More generally, Schrödinger's equation looks like this. So that is, when there's a potential, I should have an equation that has something like kinetic energy plus potential equals total energy for a particle. There are many other differential equations you could come up with. In fact, we'll do some of those on the homework. But this one has the properties that it's linear. That is, it'll be the superposition principle. If two different wave functions are both solutions, then the sum of them will be. And it has the kind of build-up, the kinetic plus potential equals a total energy, so it has some basis in a physical law. And the other thing that's interesting about it is that it clearly points out to us that the wave functions will be complex because there's an imaginary number I right there. So with this, we'll end up trying to develop a more general law, solutions for quantum mechanics using this basic law.